Hello! Today I'm going to be speaking about the golden ratio. Now I chose this topic because I find it quite interesting, how we find maths in the natural world. So this is a sunflower and these are its seeds. You can see that they're arranged in this very nice pattern, and you might wonder why they're arranged in that pattern. Well, if you're a sunflower, your primary goal is to have as many seeds in a given area so that you have as many baby sunflowers as you can, so that your species survives. Now, if we have a seed, then another seed, and just like let's say we have a bunch of seeds, if we just line them up in one direction, we're not really using the whole surface area we can. We're not using the whole circle. So the question is, by how much do we rotate these given seeds to get as many seeds as possible in a given area? Now, sunflowers have done this by natural selection. Obviously, the most sunflowers that had the most seeds in a given area survived, and that's why the arrangement of these seeds is very close to the golden ratio. So, first of all, I want you to look at rational numbers. Now that you might be thinking like, why are we going through rational numbers? Well, you'll learn shortly. Basically, what I want to show is that some numbers are more irrational than others, and for this particular problem, the more irrational our number is, the better our arrangement of seeds, because obviously if you have a number that's rational or whole, your seeds are arranged in a very specific way, so like in lines or sorts of other shapes, or if you have them separated by 1/2. The thing what we want to do is we don't really want to have like 4 lines of seeds or like 5 or 6, doesn't really matter. What we want is to squeeze as many seeds as possible in our area, and we're not really going to get that with whole numbers if the distance between this and this is going to be, let's say, 2. So what we want is the most irrational number possible, so really some really crazy number, so all of our seeds is in a different place and we get as many seeds as possible in our circle. So you might think that pi is a really irrational number because it goes on into infinity, goes as follows: 3.141592, and so on. It goes really long. Now we can describe pi as a continued fraction, which is basically we have a whole number and we add a fraction to it, and this fraction doesn't end. So we can describe pi this way: 3 plus 1/7, which is 22/7, which is 3.14. That's a good approximation, but what if you want an even better approximation? Well, we continue. Go plus 1/15 plus 1/1. So this is going to be a large number, and 1/292. This is going to be a tiny number because we're dividing 1 by a huge number. So we can stop our continued fraction here and say that we have a pretty good approximation of pi, because the numbers after this are going to be arbitrarily small. Now, what about the square root of 2? You might say that's an irrational number, and you'd be right. It's actually more irrational than pi, because this value stays constant throughout, and it's quite a large value. 1/2 is 0.5. It's a much larger number than 1/7, 1/15. So you get the picture. Now, but what about the most irrational number? Well, what would you think? If we have a fraction where 1 is divided by some number a, when is this fraction at its largest? When you could say when a is 0.01, and you'd be right, but what if we can only use whole numbers? Well, the answer would be a has to be equal to 1 for this to be the largest of whole numbers. You could say that 1 over 0, but we don't really know what 1 over 0 is, and it's not really a valid argument. So, how we're going to find the golden ratio? We're going to add to 1 a fraction where 1 is over 1 and it continues into infinity. How do we calculate this? Well, if you see here x equals 1 plus 1 over 1, and if we put another x here, x equals 1 plus 1 over 1, is the same statement as who we have here. It's exactly the same statement over and over again. So we could say that all of this is equal to x. So x equals 1 plus 1 over x. This is a basic linear equation. I'm going to multiply both sides by x. So x squared. I'm going to move these terms to the left hand side, so their sign is going to be the opposite of what it was. So x squared minus x minus 1 equals 0. Now what I could do is I could make a quadratic equation and solve it like that, but that would take ages. So I'm going to sort of using the binomial theorem, I'm going to find a pattern for this, which is going to be x minus 1/2, the whole thing squared. Is this true? Well, let's plug in the values. So x squared, I've got that. X minus 1/2 times 2 is minus x. I've got that one as well. And minus 1/2 squared is plus 1/4. Now I don't really need 1/4, so I'm going to subtract it. Minus 1/4 and minus 1 equals 0. What else can we do? We can throw this to the other side. So x minus 1/2 squared equals minus 1/4 minus 4/4 is minus 5/4, and I switched the sign because I'm going to the other side, which is plus 5/4. And what I can do is I can take the square root, because this is to the power of 2. So I'm going to take the square root, and my x minus 1/2 is going to be equal to the square root of 5/4. Now you could ask, what is the square root of 5/4? Square root of 5/4, we can write that as the square root of 5. The square root of 4 is 2. Since this is a non-equivalent operation, I have to put this in absolute value, so plus or minus 5/2. I'll throw this to the other side and we get our wonderful number, which is 1/2 plus or minus square root of 5 over 2. Now I can write that in a more beautiful fashion, where x equals 1/2 plus or minus the square root of 5. What is this number? This number is 1.61 if we're calculating it as 1 plus the square root of 5 over 2, and it's 0.61 if we're calculating it as 1 minus the square root of 5 over 2. This is our golden ratio, both of these numbers. So this is arranged according to these numbers, which I find roughly. It's very close. It's very close to these numbers. These numbers go into infinity, by the way, because they're irrational. But it's very close. And I find this fascinating, me personally. Be sure to like, comment, and subscribe. Please give me your opinion in the comments. Did you like this video? What would you change about it? tell me which topics you would like to see next. Thank you for watching and see you next time.